So we're going to start by finishing up with one topic from neural networks that we didn't get to last time, and then we're going to move on to the topic of exploration in the what's called the bandit setting. So the way that neural networks are trained is not quite with gradient descent usually, or with gradient descent. They're usually trained with a slight variant. So here is the algorithm for gradient ascent. If you replace this plus sign with a minus sign, it would be gradient descent. And an important property of the derivative, or of gradients in general, is that if you add two things and then take their derivative, it's like taking the derivative of each thing in turn and then adding them together. So if we have f of x equals g of x plus h of x, then df dx equals dg dx plus dh dx. So that's a nice property. That's called linearity of the derivative. And what it means is that we can switch these two operators, this sum and this gradient. Oh dear, we already have. Oh yeah, okay, once I just transitioned to that, it changed. Okay, so this is what we started with. We have, this is the log likelihood function, this is the log likelihood of the whole data set, because we're summing over all the data points of the log likelihood for that data point. And we want to maximize the whole thing, so we take the gradient of the whole thing. And what that's equivalent to, for the reason I just showed, is switching these. So we can move the sum to the outside and move the gradient in. And so this is really, so now we can think of this, instead of taking our weight vector and performing one gradient update, we can think of it as the sum of lots of little tiny gradient updates. Each little gradient update corresponds to one of our data points. A data point being the xi and the yi. Now, when the value of the gradient changes depending on where you are. Like if, I showed you kind of that hill last time, and the gradient is the steepest direction and how steep it is. But if you change where you are, then obviously the gradient will change. And so the idea behind stochastic gradient ascent or gradient descent is once the gradient for one training example has been computed, we might as well move in that direction and look for the gradient of other data points in that improved location, because that new location is probably going to be a little bit better than the one we were at before. So here's how stochastic gradient ascent works. Replace this plus sign with a minus sign, you'd have stochastic gradient descent. Instead of having a sum here over all of the data points, we just pick a random one and we move in that direction. And in general, this will be very noisy. You'll be moving all around. But in expectation, the expected update that you make here is equal to the full gradient. So I'll just show you this alternative before. Here we make one update where we're summing over the gradients corresponding to all the individual points. These would be this would be the direction that makes the whole data set a little bit more likely according to your weight vector. Whereas this is an update that makes just this data point a little bit more likely according to your weight vector, and then just that data point a little bit more likely according to your weight vector. And you bounce around between all the data points, and the gradients might be in different directions, but on average, the average of the gradient will be the true gradient that improves the log likelihood assigned to the whole data set. Any questions about that move? Yeah.
So I just want to clarify, when we choose this gradient, do we stick with ascent or descent, or do we mix between?
We're always picking one or the other. And it's, yeah, if you're talking about something you want to maximize, then it's gradient ascent. If you're talking about something you want to minimize, then it's gradient descent. Yeah.
Would this be slower than normal gradient descent? So like
It will tend to be faster because, well, it depends on the problem really. But the reason it might be faster, and often is that consider two possible weight vectors. One you were just at, and one was the result of moving to improve performance on a single data point. If you had to guess which of these 2 points is going to be more likely to be closer to the one you're actually ultimately looking for, probably the second one. That gets less true as you go further along in training, maybe, but probably the second one. And so then if you're wondering, okay, so where should I evaluate the gradient of the weight vector? Should I evaluate it the first one or the second one? Well, I mean, this is an iterative algorithm. You're slowly improving your best guess, and so you'll probably want to go from the spot where you know it's a slightly better guess. If you're computing the gradient for the whole thing, you basically have to compute the gradient per point one at a time, often. And so as long as you've done this already, you might as well move before going on to the next one. In fact, what I just said is not quite true when you have GPUs or any sort of parallelism. So in fact, you can often compute the gradient for, 10 or 100 or maybe 1,000, 24, or maybe more different data points all at once. You can do them all in parallel. And so then it doesn't make sense to wait until you've computed this one, move, do the next one, move, do the next one. You might as well just do as many as you can at once. And so that's a batch. And so then instead of just picking one at a time, we pick a random subset of size j. And then what we're doing is we're summing over all the data points in that subset. We compute all these gradients in parallel if we can do that. And then that's our update. So this is still stochastic because it could be any subset. We'll kind of move around a bit, but it will be a little less noisy than just doing it point by point, and it takes advantage of possible parallelism. I don't know if you guys remember simulated annealing, which was briefly discussed in one of the early lectures. When we were talking about hill climbing. But that's what that does is instead of just moving to the best neighbor, it adds in some randomness so that you don't get stuck in local optima. And I've seen some work that suggests that actually the fact that these updates deviate from the true gradient can actually be helpful. I mean, it's not just that it's like a quicker thing to do. The fact that it's a bit noisy can sometimes help you find better solutions. But the real motivation for this is that you might as well make the updates as soon as you can. Any questions about the difference between stochastic gradient descent and gradient descent or ascent? Yeah.
And also, I just want to clarify, there's thrashing if you're optimistic, is that what it's called?
Is it called thrashing? I don't think I've heard that word applied in this setting, but maybe it would work. I can't think of what you call it. It doesn't converge. It bounces around too much. Yeah, maybe there's some word that people often use, but I can't think of it right now. If you say thrashing, I think people know what you mean. Right, so we have the learning rate here as well. And technically to get convergence results for stochastic gradient descent, you need this learning rate to be going down. If the learning rate were staying constant and you get if you get to the optima, in normal gradient descent, the gradient's now 0, so you don't move anymore. But in stochastic gradient descent, that 0 might be a sum of some positive and negative numbers or like vectors going in different directions. And so if you just continued moving stochastically, you'd keep bouncing around. You'd never actually stop unless you decayed your learning rate to 0. Okay, we're going to, just really breeze past some applications of neural networks, even though obviously they are numerous. So the kind of original application that got everyone very excited about neural networks was computer vision. So there is a problem called ImageNet where you have a bunch of pictures and a bunch of labels for what's in the picture. And then you feed the idea is to come up with a machine learning algorithm that takes in this data set and then takes in new images and is able to predict the label. And so here is how things were going before AlexNet came on the scene. If we're just looking at the best ones, it was kind of not really improving much. And then people started trying neural networks, and the error rate started going way down. And if you extrapolate this out to today, it looks like the error rate would be negative. So there you go. An application that is the biggest today and may well continue to be is large language models. So here is Claude, quite impressive. I was hoping to tell you a little bit about a single attention head, but I think you guys will just have to look that up if you're interested. But I typed into Claude, can you please tell my intro to AI class how a single attention head works and how that building block allows you to be a proficient English speaker. And it doesn't actually give a hugely helpful answer. It's a bit too high level, but it attempts to say something interesting. And what this is doing, well, there's the base model and then there are improvements to it, and I won't talk about those at the moment. But the base model, what it's doing is the input is all the text that's preceded, the target is the next word, essentially, and it's just trying to predict what the next word would be if this text appeared on the internet. In fact, the fine-tuning changes that behavior in important ways, but that was kind of the major piece that got this approach off the ground. Okay, that's it for neural networks. Now we're going to talk about exploration and exploitation, and I need a volunteer from someone who has a Venmo account. There is no risk of losing any money. You can only get money. Yeah. Back there. You. Yep. If this loads. Okay. So, no. I'm sorry. I wasn't pointing at you. I was pointing at, yeah. Okay, so you get 100 clicks of these buttons, all right? You'll have to come up to my computer. And this is just to help you keep track. And with some probability, when you click that button, you get a reward of 10 cents. The probabilities might differ between the buttons. And so go ahead. You have 100 clicks. You can, once you start seeing what sort of rewards you're getting, which are down there, it'll keep track of how many. Maybe you can change your mind about which buttons are the best to be clicking. Just, click it. Uh-oh. Oh, no. Oh, it was working. The full screen thing has confused it, I guess. Okay, I'll just have to tell you guys what's happening, and you can do it on... Is that going to work? Yeah, okay. All right, go ahead. You're doing this in private. I'll just describe to you what's happening.
First I will...
Just go for it. Okay, click the green button.
5 times?
Okay, clicked it 5 times, and he's got 1 reward.
All 5 times.
Okay, clicking the gray button 5 times, no rewards. Clicking the blue button 5 times, 1 reward, okay? So 85 clicks left.
Then I'll click 10 green and 10 blue.
Okay, doing 10 more green and 10 more blue. So we've got 15 clicks for green and 5 rewards, 15 clicks for blue and 7 rewards, 5 clicks for gray and 0 rewards.
So I'll click rest of clicks on.
Okay, so the last 70 you're going to do on, or the last however many you're going to do on blue.
Yes.
Okay. So it'll tell you when to it'll stop you when you've finished. Okay. Yeah. All right. So you've got 28 plus 5 is 33 for a total of $3.30. You can give me your Venmo information and I will send that to you. And I can reveal to you that you did pretty well. This was, I mean, you ended up on the right one. That was, that seems low, actually. Am I misremembering the, I thought it was 50% you get on the blue, but you might have just gotten unlucky. I think it was 30%, 40%, and 50%. I don't know if they're using a very good random number generator on Scratch, but there you go. You got, you ended up on the right one. You did some, it made sense to try the other ones at the beginning. Yeah, just come up after and I'll pay out. Okay, so that is called the multi-armed bandit problem. And there was a trade-off at the beginning, which you saw, between going with the one that seemed best in the moment versus trying to learn more about what was going on. So to kind of review where we are in the course, we've kind of, it may seem like we've bounced around in topics a bit, but I'll just tell you about the logic of how it all fits together. So, for the question of how do you plan when you know how your actions affect the environment, that was what the MDP lectures were about. That's given a model of how your action changes the state, what actions should you plan in order to get rewards. And then the machine learning lectures were about how to learn from data how your environment works. So neural networks that I was talking to you about, but other machine learning approaches from before, like naive Bayes. They're about using data to come up with a model that allows you to predict what's going to happen in the future. And now what we're going to be talking about is how to trade off collecting data versus accomplishing goals. That's the exploration-exploitation trade-off. And then next week it'll be reinforcement learning, which is putting it all together. Okay, so the exploration-exploitation dilemma faces people who are making decisions online. That is, like, they're doing it in real time, basically. And so exploitation is making the best decision given the current information, and exploration would be gathering information. And the best long-term strategy may involve short-term sacrifices, including gathering enough information to make the best overall decisions. So some examples of this: if you're trying to select a restaurant, exploitation would be going to your favorite restaurant, exploration would be trying a new restaurant. If you are a tech company interested in showing advertisements, these slides were made in the UK, so they call them adverts, then exploitation would just be showing whichever advertisement has the highest probability of being clicked on, whereas exploration would be showing something else to maybe get a sense of whether there are other good possibilities that you don't know about yet. Oil drilling at the best known location versus drilling at a new location to learn more. Game playing the move you think is best versus playing an experimental move. These are trade-offs you have to make when you start out with no information. So I'll discuss a few different exploration strategies. I'm not sure we'll have time to get to the last one, but we'll cover a few anyway. And here's the formal setting the kind of simplest setting we can start with in which there is a trade-off between exploration and exploitation. So this is called the multi-armed bandit setting, and it is based off of the term one-armed bandit in Vegas for a slot machine. And the multi-armed bandit is if you have many different slot machines, like the 3 buttons in the example from before, and you're trying to pick which ones to play based on how much they're paying out. So we have a set of arms or actions, and then each one comes with its own reward distribution. So in the example up there, one was 30% reward of 1, 70% reward of 0. The next was 40% reward of 1, 60% reward of 0, and the third was 50-50 reward of 1 versus 0. Rewards don't have to be 1 and 0, they could be any numbers. So the distributions could be whatever, really. And then at each time step t, the agent selects an action or an arm. The environment generates a reward sampled from the relevant distribution, and the goal is to maximize cumulative reward over some amount of time. In the example we did, it was over 100 steps. Some terms we'll use for talking about how good different approaches are on this slide. So the action value, that is Q of A, this corresponds to what was called the Q state in MDPs before, if you remember that. The Q value of an action, or the action value, is the expected reward if you take that action. So in the example from there, it was 0.3, 0.4, 0.5. That would be the expected reward any given time you take the action. The optimal value is just the maximum over actions of the Q value. So whichever action is best, that action's Q value. So the optimal value in the game that we just did was 0.5 because that was the expected value of the best button. Now, the regret per time step is how suboptimal the action you took was. So this was the optimal action, this was the action you actually took. So every time the green button, the one on the left, the Q value for that was 0.3, the optimal Q value or the optimal value was 0.5, so the suboptimality was 0.2. And so there's some, if you're following an algorithm with randomness in it, then you have to take this expectation. So it's depending on your algorithm, which action you end up choosing may be random. So an algorithm for selecting AT might have some randomness. So that's why we have an expectation here. So there's the suboptimality, that is the suboptimality of the action you actually took, and then there is the expected suboptimality, which is called the regret, which is taking an expectation over what you could have done according to the algorithm you're following. And then the total regret is just summing over the whole lifetime. And maximizing cumulative reward is equivalent to minimizing total regret because it's basically just, you're trying to get as close to optimal as possible. And another way of looking at regret is each action has a suboptimality or a gap. So delta A is basically how suboptimal each action is. So it was 0.2, 0.1, and 0. 0 suboptimality means optimal. And then the count is just how many times you took that action. So another way of counting up your total regret over a lifetime is the expected number of times you take a given action times the suboptimality of that action. So this would be the number of times you're taking an action times how suboptimal it is, summed over all of the different actions. So a good algorithm, you want to have small counts on the actions that have large gaps or large suboptimalities. Pretty straightforward, obviously. But of course, the gaps aren't known. I mean, you don't know which one is the best. Otherwise, you could just pick that, and it wouldn't be very interesting. And again, this expectation is because depending on what algorithm you're following, which might depend on the random rewards that you've seen, the identity of the action that you take at time t, it's not going to be deterministic. There will be some randomness in it. So, getting linear regret is, okay, question first, yeah. So the question is, how do I identify if an algorithm is random? I'll show you some algorithms that are obviously random because there's like a step in it where it's like flip a coin kind of, and then depending on the outcome, do something. But in this setting, if your algorithm ever depends on rewards that you have seen before, since those rewards were random, like sampled from a random distribution, then the ultimate action you'll end up picking will be random. Because, I chose this, maybe it would have given me a reward of 0, maybe a reward of 1. Depending on the answer, I'd be doing something different the next step. And so then if we're thinking at the very beginning, okay, what's this person following this algorithm going to be doing at time step 10? Well, it depends on what they see in the middle. And since what they see in the middle is dictated by randomness, there's some randomness over what they're going to be doing at step 10. I'm not sure I could give you a general principle. I think in general, you just have to look at the code and the setting and then see whether it's random. Yeah, no problem. Okay. So the first few algorithms I'm going to describe are greedy, epsilon greedy, and decaying epsilon greedy, and I'll get to what those mean in a minute. But linear regret is basically very bad. Linear regret means in expectation, as time goes on, you're getting more and more regret. It's never slowing down. Like if I always just picked the action on the left, no matter what I saw, that would be linear regret in expectation. If I happened to be right, it would be 0 suboptimality the whole time. If I happened to be wrong, it would be constant suboptimality every single time. Adding it up, it goes up as a line. And so then the expectation over that uncertainty means that it would be linear regret. So what we're going to be looking for is algorithms that have sublinear regret. And this is the total regret that is being plotted. And so the per time step regret, if we have something that's sublinear, that means the derivative is going to 0. So that means as time goes on, we're less and less likely to be meaningfully suboptimal. So our suboptimality is basically going to 0 per time step. So that would be good. If this flattens out to 0, then that means we're learning. We're eventually picking actions that we're eventually not picking suboptimal actions or picking them very rarely. But I think this will become a little clearer once I talk about the algorithms themselves. But one point to make first, remember regret is the expectation of suboptimality. And so for an actual run, if you're actually playing the bandit game, the suboptimality might look something like this. You might get lucky and end up picking actions that have low suboptimality. You might get unlucky, thinking at this point in time that actually this other action is good, even though it's not very good. So the actual suboptimality will look much rougher, but an expectation will be smoother. Yeah? That's right. None of these decrease. Does it? Well, okay, I drew it a little roughly. I tried to draw it so that it never went down. Okay, maybe there I messed up. But yeah, this should always be increasing. Okay, so the greedy algorithm, its approach to trading off exploration and exploitation is it doesn't explore ever. So here's how the greedy algorithm works. You start out keeping track, just like I was keeping track below up there, of how many times you've taken each action and how much total reward you've gotten for each action. And so you start with them at 0. And now you keep repeating forever. You come up with an estimate of the expected reward for each action by taking the total rewards for that action, dividing by the number of times you've seen it. This is 0 divided by 0 at the start. It doesn't really matter. Just deal with it. Come up with some number. It doesn't really matter. And then what you do is you just pick the action that maximizes that whichever seems the best, and then you take that action. So you take action AT, whichever maximized this estimate of the expected reward, and then you get some reward that's given to you by the problem, basically. Well, it's sampled by the problem. And then, obviously, you tell this little counter that you took that action, you keep track of the rewards you got for that action, and so you update your data set, basically, about what you've seen. Any questions about this algorithm? So after about 30 time steps, maybe a little less, you were basically following this algorithm. You decided which was best. I mean, maybe you weren't continually checking to make sure that the ratio never changed compared to other ones, but I don't think it did. And then you're basically just not trying to seek more information, but just trying to do the best that you can. Okay, so this is kind of the baseline starting point, and then we'll see different exploration methods which kind of modify this basic algorithm. So this is it written out in math, which I don't think is any clearer. But I'll say down here, if you're following the greedy algorithm, you could lock on to a suboptimal action forever. So here's how. Let's say that, in the example where we had 30%, 40%, 50% chance of getting one reward versus 0, maybe you just get unlucky in the first 20 time steps, and you happen to not get many rewards when you're taking that one, and really unluckily in a way you get more rewards than you would have an expectation for this bad one. Then you would think that this one was better than that one, and so then for way into the future, you'd be spending a lot more time on that bad one, and maybe you'd never discover that actually this one was better. So if you're doing the greedy algorithm, if you're not explicitly trying to make sure that you're learning enough about the other ones, the ones that you think are probably suboptimal but you're not sure, then you can lock onto a suboptimal action forever. And because of that possibility, even if it's a pretty small possibility, a small possibility times continually increasing regret still is continually increasing regret. So like taking a line and then taking an increasing line, multiplying by 5%, it's still an increasing line. So this algorithm has linear total regret. That is the expected suboptimality because of the possibility of locking onto a suboptimal action and never correcting it. So as far out into the future as you like, you're always accruing more and more suboptimality. Here are these definitions again, in case you've forgotten them. It's kind of a lot to take in. This is the action value. This is the optimal value. The regret is the expectation of the optimal value minus the action value, and then the total regret is summing over all that time. The other term that I defined for you before is the gap, delta A. That's how suboptimal a given action is. So the actual rewards don't actually affect what we call regret. Regret is just a function of the actions and the expected payout of those actions. That's just a bit of a subtlety, which is maybe a bit confusing. So I'm just putting this clarification on this slide. Okay, different algorithm, epsilon greedy algorithm. The epsilon greedy algorithm, instead of exploring never, it explores with a fixed, maybe small probability forever. So with probability 1 minus epsilon, it picks the action that is believed to be the best. And with probability epsilon, it selects a random action. But if there's always a probability you're selecting a random action, the expected suboptimality from selecting a random action is basically the average suboptimality of all the actions. So this is the average suboptimality of a randomly selected action. Multiply that by epsilon, the expected loss is going to incorporate at least this term. And so it also has linear total regret. But let me show you the epsilon greedy algorithm in code. So the black is the same as before. The red is what's new. Here we're calculating what appears to be the best action based on the data we've collected so far, dividing the total rewards for that action by the action counts. But if we sample a random uniform number between 0 and 1, and that number happens to be less than epsilon, so that means basically with probability epsilon, then instead we change our minds and we set the action to some random action. And then that would be the one that we'd take. Any questions about how this works or anything else? Yeah.
So for RT, taking an action to take random, that's where you click the button and
Yeah. Right. So this line corresponds to clicking the button. This is like the line where we interact with the environment that we're in. Yeah.
instead of like your random action, would there be like any disadvantage to, for example, like going down the list of like saying like I guess ranking them based on their expected value and it's like exploring them further down the list?
Yes, there are much cleverer things to do than this, and we'll get to at least one that is cleverer than this. Yeah, this is like the most uninformed approach to exploration you could have, really. You're basically just saying like, maybe we should explore, and if we do, maybe we should do that. I mean, you might know things. Like in the first stage of your exploration, you were exploring them all equally. In the second stage of your exploration, you were focusing on the two that appeared to be the best, right? And so that's a much more sensible thing to do. It's kind of tailoring your exploration toward the actions that are more likely to be optimal. So the more suboptimal something is, the less time you should spend exploring. Yeah. Okay. The next approach to exploration that I will tell you about is called optimistic initialization. It's not so good, really, theoretically, but it's so simple that I'll tell you about it. Okay. Yeah, I'll just show it to you in code rather than in math like that slide. Here are the changes for optimistic initialization. I chose these numbers out of thin air. You could choose different numbers. But what's basically happening here is you're pretending that you've taken some actions and that you've seen some rewards. So this is basically imagining you've taken every action 5 times and seen a total of 10 rewards. If your rewards are likely to actually be less than this, then this would qualify as optimistic initialization. And what this means is if you haven't explored something much, if you haven't tried it many times, then these numbers will still be dominating your beliefs. And so you'll be starting out very optimistic about it, and so if you haven't done it much, you'll think the value is much bigger than it is, until you actually try it and get slapped in the face by reality and realize that actually it's way worse than that. And so what this encourages is you to spend more time on things that you haven't seen as much. Once you've seen things more, these numbers will come down, and then you'll be really comparing between things based on how well they actually perform. The initialization will get washed out. Questions on why this would have that effect, or any other questions? Okay. So when I first talked about epsilon greedy exploration, that was with a constant epsilon. And what you should really do if you're doing epsilon greedy exploration, although often people just don't. I don't like it, but anyway. is they pick a decay schedule for epsilon. So epsilon gets smaller over time. So don't worry about these numbers so much. Just focus on the fact that there's a t in the denominator here. So as time goes on, this epsilon is going down as a function of some constant divided by t. And if you do this, then your asymptotic total regret is logarithmic in nature. So that means the derivative is basically 1 over t. And so your suboptimality over time gets lower and lower and lower, and it approaches 0. So that's amazing. Setting this intelligently requires knowledge of how suboptimal different actions are. Don't worry about the details so much, although just know that there are some costs to it. What we'd like to find is an algorithm with sublinear regret without knowing anything about how suboptimal different things are. But here it is in code, the decaying epsilon greedy algorithm. Instead of having a fixed epsilon, we have an epsilon that depends on time, and that's going to be, I guess I didn't need to put this minimum in there if the starting epsilon is going to be less than 1. But it's going to be some starting epsilon divided by t plus 1. I just said t plus 1 because the convention is in Python is to start with t equals 0. So there you go. This is an epsilon t that is decreasing as a function of 1 over t, basically. And if you do this, the total number of exploration steps is actually going to be infinite in the limit, because a half plus a third plus a quarter plus a fifth, so on, sums to infinity. But it will get rarer and rarer and rarer, and so your expected suboptimality will still go to 0. So this is an approach to doing more exploration at the beginning, less exploration as time goes on, and by doing so, guaranteeing that you will eventually discover the optimal action and only take that. Or if there are multiple optimal actions, then only taking any of those. So logarithmic regret, the total regret growing as a function of the logarithm of the number of time steps you've been at it, is actually as well as you can do. So even though epsilon greedy seems really bad, and you know, we shouldn't, the constants here are not trivial, so it could be, even if the asymptotic behavior is as good as you can do, you can in practice do much better than decaying epsilon greedy. But that said, logarithmic regret in the limit is as well as you can do. I'm not going to get into the details here or tell you what this measure means, but basically this is a measure of how different the reward distributions are between some action and the optimal action, and this is how suboptimal the action is. So we're summing over all of the suboptimal actions of this ratio. This is going to be some constant. And then you have a constant times log of t, the number of time steps you've been at it, and there's no bandit algorithm that can produce a regret that is less than this in the limit. So in general, the instantaneous regret, the per time step regret, well, really, we just call it the regret, but I think it's clearer to say per time step regret. You can get it to go to 0, but in expectation, it can't be any faster than 1 over t, the number of time steps that you've been playing for. So there, I'm just showing you the terms again, in case you've forgotten them, which would be forgivable. You have the action value, Q of A, that's the expected reward for that action, the optimal value, and then the regret is the expected suboptimality, and the total regret is summing over all time. Okay, the next bandit algorithm I'm going to tell you about, racing through them, so please feel free to stop me about with questions about previous ones if you want reminders, is optimism in the face of uncertainty. And I might have time to get to another one, but even so, I think I like this one the best. So let's say we have a few different belief distributions. These are our beliefs about the expected reward from taking different actions. So put up a 1, 2, or 3. If these are our belief distributions, which action do you think we have probably taken the least to result in these sorts of belief distributions? So this is the marginal probability over what we think the expected reward for that action might be. It's quite broad. Our belief distribution over the expected reward for A1, it's narrower for the expected reward from A3. So put up a 1, 2, or 3 for which you think we've explored the least that would lead us to have belief distributions like this. Yes, I am seeing ones, and that is correct. The more you've seen something, the more confident you can be that your sample mean is tracking the true expectation. I mean, if you've taken 1 million samples from something and you've seen 500,000 times, X happens, you can be pretty confident that the true probability X happens is 50%. If you've taken it twice and it's happened once, yeah, maybe it's 50%, but who knows really. Okay, so if this is our situation and we have a long time left to go, which action should we pick? Well, maybe actually blue is the best action to pick because there's some chance that it's way better than how good we think green and red are. And so even if in expectation for this very time step we could do probably better by picking green, it's probably worth picking blue in this setting to rule out the possibility that blue is really, really good. So let's say we take blue. Too bad, it was a good gamble, but blue was exactly as bad as we thought it was, maybe even worse. And so then our distribution would move over there. It would get a little bit narrower, although that seems to be imperceptible in this diagram. And then maybe we'd pick another action. Maybe we'd pick red next. And then kind of once we rule out that red is better, then maybe we'd end up with green. Or maybe red would be better. Who knows? And so this strategy is basically being optimistic in the face of uncertainty. So here, it mattered to us more that blue could be good than that blue could be really bad, or even that blue was probably bad. So this is kind of acting as if we think we're going to be more successful than we are, or more successful than we'd really guess if we had to guess. So this is the optimism principle, and it leads to an algorithm called the upper confidence bound algorithm. So what we do is we estimate an upper confidence for each action value. So before, those algorithms I was showing you, we just take the total reward, the count of the action, we do the first divided by the second to get a sample mean, basically, an estimate of the expected reward. But now we want some more numbers to get involved. We want to think not just about what the expected reward is, but like, what could it be, maybe, plausibly? So we estimate an upper confidence for each action value. So here, this hat means it's basically an estimate. Was it a hand? No, okay. And so what we're hoping for is an estimate of the mean, but also an estimate of like how good it could be. So we want this not to be too big, but big enough that we can be pretty sure that the real action value is lower than this sum. So if we were looking at this, here would be our Q hat for green, and maybe our U hat would be like the difference between there and there. So then Q hat plus U hat would get us there, and our upper confidence bound would be there. We're quite confident that the true expected value, the true action value for this green action is less than this number. Whereas for red, Q hat might be there, Q hat plus U hat might be there, and so that might actually end up being a bigger value than it was for green. So this is what we want from our U hat, and it's going to depend on the number of times that we've selected that action. So if we haven't selected it many times, then U hat is generally going to have to be larger to account for our uncertainty. And if we've selected it more times, then it can be smaller. Yes? No, it would just be dependent on the number of times we've seen it. And the reason, okay, so the question was, if we've seen, let's say for one action, we've seen, we've taken it 10 times and we've gotten a reward of 1/2 every time. And for another action, we've taken it 10 times and we've seen 5 rewards of 1 and 0 reward and 5 rewards of 0. So those two settings have the same expected value, but the second one has more variance, right? Because there's more variance in the actual reward. But what we're interested in is our estimate of the true mean. And our estimate of the true mean will actually have the same variance in both of those cases, even though the underlying distributions are different. Our belief distribution about what the true mean is will really just depend on the sample mean that we've seen and the number of samples that are composing it. I might be too Gaussian-brained, and that is not quite true if you have belief distributions that aren't Gaussians. I'd have to think more about that, but I know at least if you're using Gaussians to represent your uncertainty, then it just depends on the number of times you've taken the action. Okay, so as you've seen something more often, then you can get away with a smaller upper confidence bound and still be quite confident that the true mean is less than Q hat plus U hat. And this leads to the algorithm of just maximizing our optimistic estimate of the value of the action. So I'll show you in code in a second. The origin of this, don't worry too much about the math, but I'm putting it here for you if you're interested in, is something called Hefting's inequality. And this is a property about how quickly sample means converge to the true expectations. So if you have a bunch of random variables that are sampled from the same distribution, and then you take the average, that is going to get close to the sample mean. And that sample mean is going to get close to the true expectation. So this is probably, if you add some u to your sample mean, the true expectation is probably going to be less than it. In fact, the probability that it's greater than it ends up getting pretty small. So as t gets bigger, this goes to 0. As u gets bigger, this goes to 0. So if you have a bigger u, or if you have more time, this number will go to 0, so then the probability of this being less than that goes to 1. And so you can be quite confident that your sample mean plus your upper confidence u is truly an overestimate of the actual action value of the action that you're taking. Yeah? The right side goes to 0 as t and u increase, as t or u increase. And so the probability, if this were a less than sign, would go to 1. So if this probability is going to 0, then flipping that greater than for a less than, which is what we're hoping for, that probability goes to 1, which is great because we want it to be true. So what we do for deriving the upper confidence bound algorithm is we basically have a probability that we're looking for, and then we solve for what u should be to make sure that we're that we are with high probability overestimating this. This is, I think, more math than we've gone into elsewhere in the course. So it is, the details of this are not going to be tested on, but I'm just showing it to you for your interest. Okay, so this, plugging in the numbers, this is the number of times we've taken the action. This is ut, which is what we're going to kind of solve for. And so let's say that we want to make sure that the true Q value is less than the upper confidence bound that we're going to come up with probability 1 minus p. So we only want to admit an error, a possibility p of being wrong here. And in fact, we'll make p go down to 0 as time goes on. So where this number t to the negative 4 comes in, I'd actually have to look at the textbook myself. But importantly, it goes to 0. We want to make sure that as time goes on, we're really sure that we are overestimating the true action value. And so plugging all this in, you get this formulation for the upper confidence on A. So you can see that the more you take action A, the smaller this is going to be. And as time goes on, if you don't take it, it will actually grow slowly. So if you never took this again, this would grow without bound, and so eventually you actually would take it again. I see lots of people in the back, but we still have a little while left. Okay, now they're running away. Sorry. Okay. So this ensures that we're focusing on optimal actions T, but we actually never do stop exploring any given action. It's just that for the really bad ones, we explore them not very much at all. So here is the UCB algorithm, well, one version of the UCB algorithm. In total, we take our estimate, Q of A, that's our sample mean, the total number of rewards we've seen from that action, divided by the number of times we take it, and then we add this term, which will mean that we're quite confident the real value is, the real action value is going to be less than this. And this achieves the kind of logarithmic regret that I told you is as good as we can do, basically, within a constant factor. There's just some really cool theory that people do about this that obviously we're not going to be able to get into. So here is the UCB algorithm written out in code. We have our action counts from before, our total reward per action. Every time we're about to act, we take the ratio to come up with an estimate for the expected reward. And now we come up with a new optimistic estimate by taking that and adding this term, the square root of 2 log t over the number of action counts for A. And then we pick the action that has the highest optimistic value. We take the action, then our game or our environment or our problem setting samples a reward for us, and then we add that into our data, basically. Okay, there is the attendance code for today. And any questions about how this works, why it works that way? Yeah.
Is this the same as like the Monte Carlo research?
It is, yeah. The Monte Carlo, the optimistic approach in Monte Carlo tree search is derived from this. I think this was done first, and then they were like, yeah, it seems like a good idea. Let's put it into tree search. Yep. The question for those of you who might not have heard is, does it have to do with, is this the same as Monte Carlo tree search? And yes, it is. There's the optimistic component in that as well. Okay. Just stepping back at a high level, going away from the math and Hefting's inequality and all that, why is optimism a good idea here? So if you're optimistic when you don't know for sure, then you check it out and you learn the truth. If you're pessimistic when you don't know for sure, you never check it out and you never learn the truth. So that's kind of the asymmetry here for why optimism promotes learning and pessimism doesn't. Can anyone remind me of the definition of admissible for a heuristic? Think back. Yeah. Yeah. Yes. Wait. No, because we're talking about costs. So an admissible heuristic is one that underestimates the cost. If you were thinking about the value, then it would be an overestimate. Yeah. Underestimate of the cost, overestimate of the value, same difference. Yeah. So an admissible heuristic has to be something that is underestimating the cost to the goal state. And so that's basically an optimistic estimate. And so it's the same principle, really. When you have an admissible heuristic, that's optimistic, and so you then check it out and get more information about what the cost really is. Okay, so I've said a lot of good things about optimism, but if there's suppose there's two environments that you could be acting in, and one environment has lots of dangers in it, lots of things that can go wrong and hurt you. One of the environment has no major dangers in it. And you have to pick before you go into these. You're going to be optimistic in one of these environments, and you're going to be pessimistic in the other. Which environment would you rather be optimistic in? Which environment would you rather be pessimistic in? Put up a 1 if you'd rather be optimistic in the dangerous environment. Put up a 2 if you'd rather be optimistic in the not so dangerous environment. Yes. I'm seeing lots of 2s. Better to be optimistic in an environment where things can't go very wrong for you. Better to be pessimistic in an environment where there are cliffs around every corner or other sorts of dangers. If you're in an environment where things can go really terribly, permanently wrong, and you're optimistic, something will eventually go really terribly, permanently wrong. So for all these, bandits are fun because you can do lots of good theory. But they can also, the sort of insights you come up with can also be pretty fundamentally misleading for acting in the real world, where trying everything infinitely often is actually a pretty bad idea. So if in your problem setting, there aren't real risks from exploration, then you want to make sure you're exploring enough to learn to be optimal. If you're in an environment where things can go very badly wrong, you actually maybe really shouldn't be optimistic, and maybe pessimism is a better way forward. Pessimism basically says you're not going to try new things unless you're pretty sure that nothing's going to go wrong. Kind of an anti-exploration strategy, but still in many contexts can be, could save your life. Okay. I think I will skip this and come back to it if we have time. It's just one other exploration strategy called Thompson sampling. It's cool. I'll leave it at that. I'll return to the value of information, which we talked about several weeks ago, because that is actually the time we've seen before about making trade-offs between we didn't explicitly talk about the trade-off between exploration and exploitation, but we talked about putting a cost on exploration, which would be most of the way along towards trading that off against exploitation. So exploration is useful because you gain information. We can quantify the value of that information, as we discussed several lectures ago. How much reward would a decision maker be prepared to pay in order to have that information prior to making the decision? And so then if your value of information is high enough, you can decide to collect that information. Otherwise, you can just say, I'm fine not knowing. It's not going to probably matter to me. And this is what you'd have to do to trade off exploration and exploitation optimally. But as you can imagine, coming up with optimal trade-offs between exploration and exploitation, rather than the heuristics I've shown you, is computationally just extremely difficult. All's well and good if you're just playing a game and you can press whatever buttons you want and maybe get some money. But if you were actually if you're on your 12th action and now you have to actually compute what is the best choice for me to do, trading off the information I'd get versus, the cost of doing what might not be the best, that would just be a tremendously difficult thing to calculate optimally. Okay, so that wraps up the simplest bandit setting, where basically every time you act, you're in exactly the same spot. But in the real world, when we are acting, we end up acting from different positions. So it's not the case that every time we act, we're facing the exact same decision as we've always faced. In the real world, we have context for our actions. And so the generalization of bandits that we're going to talk about now is called contextual bandits, where you don't just have actions you can take. There's not just a reward distribution based on each action. There's a state that you observe. You're in some state, and the reward will depend both on the state and the action that you took. Again, these reward distributions are unknown. You have to learn from experience. So at each time step, the environment generates a state. That's going to be ST sampled from some distribution. Then you, the agent, will select some action. And then depending on the state, depending on the action that you took, the environment will randomly sample some reward. And again, the goal is to maximize the cumulative reward. And showing banner ads is like this. If you're a website showing an ad, the probability that a user will click on it depends on the user that's sitting in front of the computer. So, and if you know things about the user, then that knowledge would help you show an ad that is more likely to be clicked on. Maybe a bit nefarious, but it is an interesting problem. So here is an example with showing, let's see, was there anything else no, okay. Here's an example with showing movies. So let's say you're Netflix, and you're trying to recommend different movies for people. So the state is which user is in front of you. The set of actions you're considering is actually very large. You could recommend any movie out of your whole library. The approach, well, I'll only tell you kind of one approach for solving contextual bandit problems, will involve first making a feature vector for the state and action. So these are features of the user. The user is the state here. So the feature vector that I came up with, keeps track of all these features. How many of each kind of movie has the user watched? Okay, they've watched none of any of these kinds of movies. So that's the state that the Netflix recommender system is operating in. And there are loads of actions, loads of different recommendations that they could make, but let's come up with features for all of those different actions. So, okay, here's a movie it's thinking about recommending. How many Oscar nominations has it got? None. What year? 2008. Does it have Will Ferrell vibes? Yes. Is it slow pace? No. Is it an action movie? No. So you're turning a state-action pair into a feature vector, and then you observe the reward. Okay, Netflix showed this user that movie, and they clicked on it. They decided to, I did it slightly differently. They watched it. So the reward was 0 for not clicking, 1 for watching, -1 for watching partway and quitting. Maybe this is what Netflix is optimizing for. I don't know. So this is this kind of data that would be collected that could be used to make decisions about, okay, a new user comes in, here are the features of that user, how many different kinds of each movie have they watched, here are the different actions I'm considering, what is likely to be the reward that would be achieved by showing them that movie. Any questions about this setup? I know it's a bit unusual to think of a user as a state, but many companies do think of you that way. All right. Okay, so here's linear regression again, which I talked to you about a little while ago, not so long ago, really. In this setting, we have an action value that is a function of not just the action, but also the state. So this is the Q value of the state and the action, the expected reward from taking that action from that state. And then we can estimate the value function with a linear function approximator, that is linear regression. The symbols used here are slightly different. We used W before, but here it's theta. But it's the same thing. It's just linear regression. Here's how you calculate it. This is the same thing when I showed you that big long derivation of how you compute the answer to linear regression. And don't worry, you don't need to remember it. And what we can do if we're in a contextual bandit problem is not just linear regression, we also might be interested in an optimistic estimate. So in linear regression, what we've talked about so far, it's just coming up with a mean estimate. But in this problem, we don't necessarily want a mean estimate. We want an overestimate sometimes. But luckily, linear regression can estimate not just the mean, but also the variance. Here's, if you're interested in finding code that does this, the sklearn library, if you do linear regression with that, it'll give you not just the best fit line, basically, or best fit hyperplane. It won't just give you the coefficients. It will also give you some estimate of their uncertainty. And then you can use that to come up with an upper confidence bound by increasing the estimate in kind of regions where you have less data and being closer to the mean in regions where you have lots of data. And so the uncertainty bonus you add will generally be proportional to the standard deviation of your prediction. And there's a geometric interpretation of that you can look at if you like. Okay. These exploration-exploitation principles can also be applied to MDPs. So when we talked about MDPs the last time, so this is moving beyond bandits back into MDPs, but when we talked about them before, the MDPs were known. You're given all the transition probabilities and asked to come up with a policy that optimizes reward. In the real world, if you don't know the transition probabilities, then you have to explore to build those out. And so reinforcement learning, which we'll be talking about in the coming week, is about not just how to compute the optimal policy in a known MDP. It's not just about how to trade off exploration and exploitation when there's one state, which is in the bandit setting. Reinforcement learning regards when the reward function is unknown and when we're in an MDP and we don't know the transition function or the reward function. So that's what we deal with next. So like the greedy bandit algorithm, here is an analog for a greedy RL algorithm. Let's say we have a finite set of states, a finite set of actions, and let's say for simplicity that the reward only depends on the new state that we transition into. So then we might do very similar to the greedy algorithm I showed you before. We just keep counts of all of the transitions that we've made. So for every state, action, new state that we've seen when we're traversing our MDP, we keep a count of it. We keep a count of how many times we've been in each state. We keep track of the rewards we've gotten in each state. And then we start. We get an initial state S, and then forever we estimate a transition matrix from the transition counts. We estimate a reward function from the state counts and the rewards by state. And then we pretend that's the MDP we're in. We solve the MDP. We get a policy, and we act according to that policy. So every single time we act, we basically forget everything we've learned, recompute everything we've learned, solve a whole new MDP, and then act in it. And then we take the action from that state, we submit that to our environment. Basically, the environment gives us back a new state and a reward, and then we tell our data sets what we've learned, that we've just taken that transition, that we've just entered that state, that we've just gotten that reward, and then we repeat forever. So that would be the greedy RL algorithm, essentially, in a finite state space with finite actions. Yeah?
Would we not also want to check the reward by action as well?
Yeah, so when we talked about MDPs earlier, the reward could depend on the initial state, the action, and the state we're transitioning into. For simplicity for this, I just said reward is only depending on the state you transition into. And so if you're in that setting, then this is enough information to track. Okay. We could do optimistic initialization in this setting by basically by pretending that we've seen really high rewards in every state. Sorry, no. It's not quite that. There's one state that we pretend we've seen a really high reward in, and we pretend that we've transitioned into that state from every state action pair. So we add this fictitious state, the heaven state, to our set of states, and we say that we observed a maximal reward in that heaven state. We just pretend that we did. And then for every state, for every action, we pretend we've observed that taking that action from that state took us to heaven. And so now we're really optimistic about every state action pair. We're thinking, oh, the only time I've done this, it took me to heaven. From heaven, you get the maximal reward and you stay there. And so we think every state action pair is going to be really good until we take it and we're slapped in the face by reality, and then we get a more accurate estimate and it comes down. So this is equivalent to optimistic initialization. It leads to something called the Rmax algorithm, and there are some interesting things that have been proven about this algorithm. So that is a discussion of exploration and exploitation. I'll take questions for a couple minutes on anything we've talked about so far or anything from earlier in the course. This will set you up to talk about more advanced RL algorithms next time. So any questions about this or about any of the bandit algorithms? Yeah?
So is exploration kind of more optimistic and then exploitation is more pessimistic?
Exploration is definitely more optimistic, and then exploitation, I'd say, is neutral. Yeah. You're just taking your best estimate so far and optimizing according to what, basically, yeah, you're just taking your best estimate, and your best estimate is going to be neutral when you're exploiting. Yeah. Any other questions? All right. The next two lectures will be from Cam, and then I'll give you one more lecture later that will not be tested on. Won't be in the homework, won't be in the final, but hopefully you find it interesting. All right, see you guys.